Dr. Anna is a principal scientist in the Department of Water Resources, Rock Applied Sciences at the South Florida Water Management District. She has an experience of greater than 20 years working both academic research and the field research. So currently she's based at the West Palm Beach area. And without wasting more time, kindly help me welcome Dr. Anna to give us a presentation.
Thank you, and once again, our apologies for, unfortunately, we have some issues with technology. I knew that one day we were going to lose to technology, so it happened finally. So I'm just gonna give you a short overview of our integrated Lake Okeechobee Cyano-HAB monitoring and mitigation program. But before we go into the details, I want to first introduce you to the problem. Why do we have blooms on the lake? Why they're so intense? Where the problem came from? Why the system is imbalanced? Because that's where usually the blooms happen in imbalanced systems. So we are going to first look into history of the changes that happened around the lake over the last 150 to 200 years. And it all started with development around the lake. Do we have maybe laser pointer? No? But anyway, so all of you are probably familiar with the two maps that you can see on the left side of the upper left corner. So basically, originally the system was looked completely different than what we have right now. Which one? Okay, this is okay. So here's the natural system. So originally the water was flowing from the Kissimmee River Valley to Lake Okeechobee and farther south into Everglades system. Right now we have completely managed system. So there's still flow via C38 canal into Lake Okeechobee and also other creeks that were converted into the canals. And the flow comes from those canals as well into the lake. But most of the outflow is right now into the Caloosahatchee and St. Lucie estuaries, and very little water is coming into the Everglades. So the whole system was completely altered over the last 200 years. So on these maps, this is the original map of the lake, how the lake looked like. So you can see that the lake was much larger than it is today, and it was surrounded by extensive wetlands. Not sure what that is, but let me just move it somewhere. All right, that should help. So this is basically how the lake looked like right now. Now this doesn't work. I apologize. I don't know what is happening with this. Yeah, that doesn't work either. So anyway, I will be loud. There's another one. Keep it coming. Something is gonna work. I don't know what is happening today. Okay, let's try this one. Here we go. We have more of those. Anyway, so this is basically how Lake Okeechobee looks like today. Okay, it doesn't work, so it doesn't matter. I'm gonna just shout. So the lake is right now completely surrounded by a dike. It's called Herbert Hoover Dike. And so we can see that we lost a lot of wetlands, and it's a completely managed system right now. Compared to what we used to have before. It all started in the settlements in 1800s and 1900s. And the settlers were building they built initially a very small earthen dike that they thought was going to protect them against flooding during the hurricanes or during even regular wet seasons. But unfortunately, when the hurricanes of 1928 and 1926 came, the dike was completely destroyed and the whole area was flooded and thousands of people lost their lives. So in the 1930s, the government decided to build a much stronger, taller dike that surrounded the southern part of the lake, and also area between the Kissimmee River and also the Taylor Creek Nubbing Slough region. So basically, that was done to protect farmlands to the south and to the north from flooding that occurred, something that could occur again after hurricanes. But then the hurricanes of 1947 came, and the same happened. Again, the whole southern system was completely flooded, and also the farmlands around Lake Okeechobee was again affected, and people lost their lives. So in 1960s, we have next phase of dike construction. So that was part of the first phase of the Central and Southern Florida project. And after that, the whole lake was pretty much surrounded by what is right now known as the Herbert Hoover Dike. The only natural flow that we have right now is the flow from the Fishiting Creek. So basically, that's the natural, the last natural flow that we have. The rest of the creeks and the river was completely channelized, practically converted to the canals. So those alterations had significant negative impact on lake ecology, hydrology, and also created problems with the blooms. So what happened? So this is the system. This is how basically the system looks like now. So all those tiny symbols that you can see, those are the culverts, the spillways, navigational locks, and pump stations. And the blue lines that you can see, those are canals. So you can see how complex the system is. It was much simpler prior to modifications and dredging. And you can see that the area of the lake significantly decreased from about 1,200 square miles to only about 730 square miles right now. So we lost all the wetlands to the west and to the south that would normally collect excess of water. When the lake reached this capacity, the water would spill, and basically the wetlands would remove excess of nutrients and sediments. So that was gone after the lake was encircled by Herbert Hoover Dike. So now we have highly managed system, and the biggest so all the biggest outflow structures, which is one is here, it's called Port Mayaka or S308 structure. And that structure releases water into C44 canal that connects the lake with St. Lucie Estuary. And on the other side, we have another structure, Moorhaven, which is known as S78 structure. And that structure basically connects the lake with C43 canal that connects the lake with the Caloosahatchee Estuary on the west coast. So that's where the major, most of the water goes into the west and east coastal areas. And very little is released into the water conservation areas. So the conservation areas have capacity that is well defined. And so there are limitations how much water can be released farther south. So the system is completely managed, and it's mostly managed. The structures are and locks and dams are usually managed by Army Corps of Engineers, and the southern structures are managed by the district. So, but you know, and they're managed according to the well-described regulation schedules. So there's a decision tree that is used based on the level. The stages in the lake will define how much water will be released and where. So when there's a specific level, let's say we have excess of water, then the water managers are, based on the regulation schedules and guidelines, are deciding where to release water and how much water should be released into certain areas. Also, another thing that changed is the were the nutrient loadings into the lake. So once that whole area was urbanized and we had this agricultural development, that resulted pretty much in eutrophication of the lake. So channelization of the originally meandering Kissimmee River, so Kissimmee River was converted also into the canal, and that not only increased the amount of water that was entering Lake Okeechobee, but also increased the nutrient loadings that entered the lake. And on top of that, we also get a lot of sediment. And so we have also certain parts of the lake have excess of unconsolidated mud deposits that have a lot of nutrients. You probably heard about legacy phosphorus in the lake. It's a huge problem. And in the past, those sediments in the lake were sinks of nutrients. And right now, they are sources of nutrients. So not only we are getting nutrients coming from the watershed via canals, but also we have nutrients coming from sediments within the lake. So we have internal and external nutrient sources. So this is basically what is feeding the blooms on the lake. But not only the concentration of the nutrients changed, but also the ratios between nitrogen and phosphorus. So the proportions between those two changed, and that basically affected the community composition of phytoplankton communities. So we had switched from communities dominated by green algae and diatoms to communities dominated completely by cyanobacteria. And most of the cyanobacteria that form blooms in Lake Okeechobee are dominated by Microcystis aeruginosa, which is a toxin producer. They have different strains of Microcystis aeruginosa. So there are strains that produce toxins, and there are some strains that don't produce toxins. And so basically, whether the strain is toxin producer or not, that is also determined by the amount of nitrogen that what we have in a system. So nitrogen is actually very important. It's not the phosphorus. Phosphorus, of course, is causing problems with eutrophication, but nitrogen is extremely important for cyanobacteria because they're species that rely on nitrogen in the water. So some of them can also fix nitrogen from the atmosphere. They're called diazotrophs. And there are some that cannot fix nitrogen from the atmosphere. So they're only relying on nutrients in water, whatever is in the water. So Microcystis aeruginosa is a non-diazotrophic species. And that means that it relies on nitrogen in the water. And during the summer, the system becomes severely nitrogen limited. But guess what? This species is so strong. I call it a super species because it can even thrive and form blooms under nitrogen limited conditions, which we have during the summer. So it's a super species, and I will explain that in a second. So harmful algal blooms are pretty much an indicator of an imbalanced system. And Lake Okeechobee is an imbalanced system because of the urbanization and development of agricultural fields and complete alteration of how the lakes functions and the whole hydrology in watersheds surrounding the lake. So the blooms are naturally occurring phenomena. So in a systems that are balanced, you will also have blooms, but they will not be intense blooms. And they always happen during the summer, but the degree, the magnitude of the blooms will change in imbalanced system. In imbalanced system, you will have very severe blooms, and this is the case in Lake Okeechobee. So why Lake Okeechobee is such an ideal aquatic system for those blooms to develop? And well, it's because there's a lot of nutrients in the system. That's first. And the western part of the lake is pretty shallow and warms up pretty quickly. There's enough light for blooms to form. And that is actually different from the central part of the lake, where we have those unconsolidated sediments that can be disturbed easily by even weak winds. And when that happens, that creates turbidity, and turbidity inhibits the growth of cyanobacteria in that central part of the lake. But the littoral zone is a completely different story. There's enough nutrients, we have enough light, and the water is warm. And Microcystis aeruginosa usually likes a hot environment, and that's exactly what we have in a lake. So temperatures in the summer usually even exceed 30 Celsius, but anything above 25 Celsius would be an ideal, optimal condition for Microcystis aeruginosa blooms. And this is exactly what happens. One more thing that is important for bloom formation is the water residency time in a lake. In a lake, water sits for more than 2 years. So we are receiving a lot of water, but that water is, the amount of water that we are releasing is not the same. We have some evaporation. So, if you look at the water budgets, so we're receiving a lot of water, we're losing a lot of water via evapotranspiration, and some of it is also released. But the residency time of water is really long, and that basically allows algae to get all the nutrients from water column all the time. So we actually can have blooms even during the dry season, which is usually colder, but during the warmer dry seasons, which is basically the winter in Florida, we also can have blooms. So it's just a perfect environment for a bloom formation. Okay, so those are the priority research focus areas for management and management strategies for harmful algal blooms. So what do we do and what do we care about? First of all, is bloom detection and monitoring. So for bloom detection, we use different products, and they were developed by agencies like NOAA, NASA, USGS, EPA. The one that I use, and my preference is the NOAA product, is called CI Cyano. And so the NOAA maps, CI Cyano maps, allows us to track the hotspots where basically the highest concentration of cyanobacteria occur on the lake on daily basis. So the satellites keep working every day, right? But we collect all water only twice per month during the wet season and once per month during the dry season. So we don't have information about the blooms in between those dates, but we can use NOAA satellite products to track where the blooms are and how intense they are pretty much on daily basis if they are not covered by the clouds. Okay, so there's some limitations, but they're very, very useful products for us for tracking and detecting the blooms on daily basis. So we also sent, during the bloom season, we also sent groups of contractors to our priority areas, and those priority areas would be the outflow structure, because our goal, the most important goal for the district is flood prevention, so flood management. And the other goal would be for us to prevent transport of potentially toxic blooms, because they're not always toxic, but prevent the transport of potentially toxic cyanobacteria biomass to downstream ecosystems. And to do that, we have many different, we use many different strategies to prevent that transport from happening. So another priority is, of course, the data collection. So we have continuous monitoring stations, so 6 continuous monitoring stations on the lake, and we have 32 routine monitoring stations. So like I said, we monitor twice per month during the wet season, once during the dry season. And all that data later is used for modeling, development of forecasting tools, and also data mining to better understand what is driving the bloom dynamics. So basically, data mining is another priority that we have. So I pretty much work with data all the time. And we also try to understand the biotic and abiotic controls of the blooms and bloom dynamics, but also toxin dynamics. Okay, it's also another topic that stakeholders care about. Next focus area would be prevention and mitigation. So I'm not going to discuss prevention, our prevention strategies, because it's it's a long story, so I'm going to leave it for another presentation. But we also engage in we have short-term strategies to deal with the blooms that develop, and to prevent them from transporting, to prevent the transport of the blooms to downstream estuaries. We use different mitigation strategies, and I will talk about that later during the presentation. And the last thing that is kind of still kind of a work in progress is forecasting. So what is important for agencies like us, the district, and Army Corps of Engineers? We want to be able to forecast where the bloom is going to be 3 days from now or 5 days from now, based on the conditions that we have right now. So that is going to be helpful for us in operational decision making. So remember that the only thing that we do, we manage water resources throughout South Florida. So we want to know if the blooms is sitting near the major outflow structure. Obviously, we're not going to open that structure and let that bloom out. And in order for us to not to do it, we have to know where the bloom is. And it would be good to know, good for us to know, have that information in advance. So now we have different groups, university and research agencies like USGS or NOAA that are developing those forecasting tools that we're hoping to use during the next wet season. Okay, so let's talk about the bloom detection. So like I mentioned, the major bloom forming species in Lake Okeechobee is Microcystis aeruginosa. And what is interesting about this species, it has gas vesicles inside their cells. So that allows the species to move up and down within the water column, which is why they pretty much outcompete other cyanobacteria and other algae. They pretty much shade them and they compete for resources. They pretty much easily outcompete them because they can move up and down and position themselves in a water column where conditions are optimal in terms of light and nutrients. But they often form these gigantic colonies that form aggregates near the surface. So those surface cones are really well visible from the air and by satellites. So this is a picture that was taken by US Geological Survey. And this is exactly how those blooms look like. They're bright green. They're really well visible. And they're even better visible when we have calm wind conditions, when there's very little small precipitation. And also we have low lake stages, turbidity is low. So then, they just basically position themselves near the surface and they're really well visible. And this is a key for the remote sensing technology. So like I said, so this map is basically what NOAA produces, and I included link here so you can actually visit the website. So this is CI Cyano product, NOAA product. And you can clearly see the redder the color, the higher the concentration of cyanobacteria cells. And so we get those maps on a daily basis, so we can track where the highest concentration, where those hot spots are on the lake. So what we can do, we can distinguish between algae in general by looking. So algae have, obviously all algae and cyanobacteria have chlorophyll A pigment, but cyanobacteria have also phycocyanin pigment. And so basically they absorb and reflect the light differently. So the satellites are collecting this information, and NOAA developed an algorithm that they're using to produce those maps. So what we can distinguish is that what is blooming on the lake in terms of, is it cyanos or something else? But we cannot distinguish what species is forming the bloom. We also cannot tell from the satellites whether the bloom is toxic or not. Because that depends on a strain of species that is present. Is it toxin producer or not, right? So that will determine, but we can say it from the satellite mice. So we actually have to measure toxins in the water using different methods. So those products, however, also have limitations because when there's a heavy cloud cover, we can't really see them that well. So, but they're usually, most of the maps are of pretty good quality, so we can easily track the blooms on the lake. Okay, so this is basically the 2023 cyanobacteria bloom season on NOAA satellite map. So you can easily see how the blooms developed, and also the locations where the concentration of the cells were the highest, and when actually the bloom ended. So usually the blooms start at the end of the spring, around, I would say, around end of April. And they last until the end of October, sometimes even longer. It all depends on water quality conditions and whether, and obviously also the weather conditions. So for example, last year, we had Hurricane Ian, which severely affected Lake Okeechobee. And that pretty much killed all the blooms. But you can very well see where the blooms were occurring during this wet season. So the bloom patterns that you can see on those maps are driven by winds, precipitation, nutrient concentration in water, light environment is also important. Hydrodynamics of the lake is very important because lake has really strong currents and they're kind of clockwise, moving clockwise. So that would also help to move the biomass that surface come around the lake. And also our operations are affecting. So the inflow points are going to be places where nutrients are delivered, but the blooms are not necessarily going to form near the outflow points. And that's because there's like, I was just telling students during the lunchtime that, for example, C38 canal, the flow rates can change quickly within a day from, for example, 500 CFS, cubic feet per second, to 20,000 cubic feet per second. If, let's say, we have a hurricane coming, our priority is always going to be flood protection. So we have to release the water no matter what, and that is going to affect the bloom patterns in the lake. So there are many different factors that are driving bloom dynamic. There's never one factor, not just nutrients, not just light. There's multiple factors that work together to determine whether we are going to have blooms or not, what types of blooms we are going to have, and how long they're going to last on the lake and where. But winds are really important because remember, those are surface patterns. It's a large, shallow lake. So the depth is like up to on average 2.5 meters, which is really, really shallow. So when we have windy conditions, that surface biomass will be moved around the lake. So sometimes, let's say if we have prevailing winds, which actually happened this year during this year's bloom season, we had prevailing winds coming from the west for several days. So all the blooms were accumulating along the east coast, which was not a good news for us because that's where the major outflow structures are. So you can see actually here, you see that red color. This is basically that very thick biomass, cyanobacteria biomass accumulating against our structure. So not a good news for us. Okay, so this is example of post-Hurricane Ian conditions. So we had some blooms before the hurricane, and but increasing turbidity because of wobbling of the lake. The water in the lake is pretty much, we have the sage is forming on the lake, so water is literally wobbling in the lake. So we can have increase in stages, when the winds were coming from the south, the stage increased by 6 meters or even higher in northern part of the lake, while the bottom was almost completely exposed. We had dead fish lying, they suffocated because the bottom was completely exposed in the south because of those prevailing winds coming from the south. But then the stage is stabilized, but they wobble. And that is creating a lot of turbidity, and you can see it on the graph. So the average turbidity increased. So this is just comparison to last year versus 2023 wet season. So one more thing I should probably mention is that the district operates in water years, not the calendar years. So the water year starts in May and ends in April. So for example, right now we are in a 2024 water year. So it started in May and it's gonna end next year in April. So even though we are not in a calendar year, but we are in a water year already, 2024 water year. And the wet season starts in May, lasts until the end of October. And then from November until the end of April, that's when we have a dry season in Florida. So we operate a little bit differently. So because of the increased turbidity, this is the second day before after the hurricane. So the light environment was really poor. And this is basically what was limiting the growth of cyanobacteria on the lake. They literally, the blooms after the hurricane dissipated within 3 weeks. And that was it for the season. Okay, so here's our expanded monitoring on the lake. So like I mentioned earlier, this expanded monitoring was created in March of 2020, but we did have 19 original sites with water quality data dating back to late 70s or early 80s. But we added additional 13 sites thanks to Governor DeSantis' Executive Order 1912. And in March of 2020, we got more money for monitoring from the state. And now this is basically, those are all the sites that we collect data from. And the little buoys are the locations where we have continuous monitoring stations on the lake. And all that data is available to the public via our DB Hydro database. You can easily access this. If you go to a district website, you can access that data. It's available to everybody. And so we collect typical physical, chemical, water quality conditions data, but we also collect samples for toxin analysis. And the toxins that the analysis that we perform right now are, we're looking at the concentration of microcystins, cylindrospermopsin, anotoxin A, and nodularin R. But most often, the toxins that we most often record on the lake are microcystins toxins. There are multiple congeners that we are looking at. It's not just one. We are looking at multiple congeners, and we also estimate concentrations of total microcystins toxins. And those analyses, the toxin analysis, are done actually by FDP, while water quality and nutrient analysis are measured by the district. And we also collect samples from this green sites. So those are the sites where we collect samples for phytoplankton analysis, and they can be qualitative or quantitative. And we also collect samples for just looking at the dominant taxa. So basically, the FDP staff takes the sample, look quickly under microscope, because what we care about is a quick data delivery, so we can communicate with the stakeholders what is actually blooming on the lake. So more complex genetic analysis they're not only expensive, but they also take time. So our goal is to deliver information quickly to the public. So that's why we did the quick assessments, but we also send samples to FDP for enumeration. So they are looking at, they literally perform counts under microscope. It's a very tedious work. I'm sure for those of you who are working on microscope, you know how tedious it can be. So we have to wait sometimes for this quantitative data for 3 to 4 months. But it's a cheaper way of getting at least some information about species that are forming or present in the water column than more advanced methods that are also available. We did some short projects on the lakes on the lake using those more advanced approaches, but unfortunately, neither the district lab nor the FDP lab has the equipment set up for this kind of analysis yet. But hopefully, we will be able to conduct those analyses in the future. So basically, this is a collaborative effort between FDP and the district. Okay, so based on the data that we collected so far since May of 2020, or we can actually distinguish three major zones and 9 site clusters with distinct water quality conditions. So guess what? The community structure and the toxin dynamics will be governed by different water quality conditions in those different regions of the lake. So we don't, the same factors are not influencing communities the same way in those different regions of the lake. So it's a very complex system, and it's a very dynamic system. But basically, this part of the lake, the northwestern part of the lake, is very shallow, warms up quickly. It usually has better light environment. So that's where we have really intense blooms on the lake. That's where they form. And then we have intermediate zone, which has also a lot of nutrients. It's a little bit deeper, a little bit more turbid. So, but we still have some pretty large bloom accumulation in that part of the lake. However, this part of the lake is a completely different story. And this is because of this thick mud deposits that get easily disturbed during the windy conditions, which affect a light environment and also water chemistry. So the blooms and the growth of basically algae and cyanobacteria are inhibited by light, not by nutrients. There's plenty of nutrients there. Water is warm, but the light is a factor that will be limiting the growth of cyanobacteria in this part of the lake. So let's take a look at the blooms. So how we define bloom in Lake Okeechobee. It might be shocking to you, but we can have values, chlorophyll A values exceeding 600 micrograms per liter. Just for comparison, I was working for over a decade in Florida Bay and Biscayne Bay. So the concentrations in Biscayne Bay are maybe up to 10 micrograms per liter. So you can see how huge the difference is. So and it's because this lake is really eutrophic, it's hyper-eutrophic actually, and so the concentration. So chlorophyll A, anything above 40 micrograms per liter of chlorophyll A would be considered a bloom condition on Lake Okeechobee. However, remember those criteria are different for different systems. So this value should not be used in other systems. So every system has their own criteria that were defined by FDP. For lake, it's a 40 microgram per liter chlorophyll A. So chlorophyll A is a proxy that is used to, so it's a proxy for total phytoplankton biomass. So we can assess total phytoplankton biomass by measuring concentration of chlorophyll A in the water. So you can see that the green bars on the graph indicate the number of sites per sampling event that had bloom conditions, okay? So you can see that proportion of how many sites out of the 32 that we sample had bloom conditions, okay? So you can see that the number of sites with bloom conditions vary by year, they vary by season, and they vary by site. So there are significant spatial and temporal differences in total phytoplankton biomass and community structure, which I will show you a little bit of that in a second. And so here is a comparison between how many blooms we recorded during each wet season. So water year 2021, 2022, 3, and 4. So that's basically, we have 4 years of data. So you can clearly see that last year was really bloomy. So we had more blooms detected on the lake, but guess what? You will see in a second that those blooms weren't really toxic. However, this year was a completely different story. And we had similar conditions to 2022 and 2021 water year. And those years have really toxic blooms. And that is basically whether the blooms are toxic or not, will depend especially how much nitrogen will have at the beginning of the wet season. Okay, so on this map again, so I basically calculated since May of 2020, when we began the monitoring, which sites had most of the bloom conditions. So you can clearly see that those northern sites are the sites where we recorded bloom conditions more frequently compared to, for example, that really muddy zone that we have in central part of the lake, where the blooms are limited by light. So basically that part of the lake has more blooms, simply because this is basically where water enters the lake from the canals. So all the water is getting from the northern part of the systems via Indian Prairie canals, Taylor Creek Napping Slough, and the gigantic C38 canal, formerly known as a Kissimmee River. The southern canals, those are outflow canals, so that's where the water gets from the lake into the Everglades. And then we also release water via S77, which is the Moorhaven, and S308, which is the Port Moyaca, and that goes east and west into St. Lucie and Caloosahatchee estuaries. So completely different patterns, and these are same situation with toxins. So we use certain standards to define whether, how severe the toxicity of the water is. So we use the EPA standard for recreational water, and that is 8 micrograms per liter for microcystins, toxins. So basically, it's the same thing. I calculated how many times since May of 2020, how many times we recorded toxin concentrations above 8 micrograms per liter, above that EPA standard for recreational waters at each of the sites, and how many times we recorded toxins in the water overall, like were they detected or not. So you can see that pretty much the sites near the inflow points have we recorded toxins slightly less often. Oops, now we are gonna run out of power. Oh, thanks God, we have okay. So anyway, and then, so this is basically also comparison between the years. So you can see that this 2023, you remember I said that was a really bloomy year, but it wasn't toxic. So that year wasn't toxic. So we detected toxins, but only at 15% of the samples that we collected since May of 2022. So basically that year had blooms, but they weren't toxic. And the concentration, if we detected the blooms, they were way, way below the EPA recreational standard. So pretty good year. This year was a completely different story. The worst year, I think, was water year 2022, which would be the bloom season of 2021 in calendar years. Those years, 2021, 2022, and 2024, there were toxic blooms that we had to deal with. And so each year would be different. And like I said, the water quality conditions would determine whether the blooms are toxic or not. So here's a comparison between number of times we detected blooms versus number of times we detected microcystin toxins. And so basically you can see that the microcystin toxins are not always recorded at sites that have bloom conditions. They can actually be recorded anywhere. You can have concentrations below 40 micrograms per liter, but still there will be Microcystis aeruginosa that is producing toxins. So it doesn't matter whether the concentration is high or not. If there are toxic strains in the water, you will find the toxins, whether you have the bloom or you don't have the bloom. So there's in most cases, we don't have very good relationship between toxin concentrations and chlorophyll A concentration. However, that will also depend which region we're looking at. So here's the map. I just did simple correlation, Pearsall correlation between the toxins and chlorophyll A. So you can see that this northwestern region, which has really intense blooms, so basically that tells you that even though the chlorophyll A is increasing, it can be high, the increase in chlorophyll A will not mean necessarily that we will see increase in toxins. However, that is a different. We see a different story in that central and central south and eastern shoreline area, where usually the higher the chlorophyll A, the higher the toxin concentration. And remember that this actually part of the lake has elevated nitrogen in the water. And the molecular makeup of microcystin toxins is nitrogen rich.
So for Microcystis aeruginosa to produce toxin, it needs a lot of nitrogen. So, so when we have a lot of nitrogen in the system, there's a higher probability that we are going to have also toxins in the water. And remember, I also mentioned that Microcystis aeruginosa can thrive even under nitrogen-limited conditions, even though it needs it. Well, it's because it stores a lot of nitrogen in the cells. So when the cells decompose, the nutrients can get recycled, and that pretty much sustains the Microcystis aeruginosa blooms pretty much throughout the bloom season. So it's a pretty tough species. Oh, and this is also the biovolumes of cyanobacteria and versus toxins. So you can clearly see that the high concentrations of cyanobacteria will not necessarily mean that we'll also have high concentrations of toxins. So the 2022 water year, the last year, or 2023 water year, was the year where we have lots of cyanobacteria, but we didn't have toxins. And this is because we have, at the beginning of the wet season, we had less nitrogen in a system than, for example, this year, we broke a record this year compared to previous 3 years. We had a lot of nitrogen in water at the beginning of the wet season this year. So at the beginning of the season, I knew already that we will be in trouble. And that was the case. We had really toxic blooms this year. So here is just looking at the dominant taxa. So like I said, it's a qualitative assessment, quick assessment, what is actually in the water. And so you can see I compared Microcystis aeruginosa. We also often have mixed communities. We can determine what is actually dominant. And we have other taxa, which are listed here under the maps that we can look at. So we often record also Cylindrospermopsis raciborski as a dominant species, Dolichospermum circinale, and probably those names changed, taxonomic change, names changed, but I'm using the old names. We can also have co-dominant species. But during the windy conditions, like we had last year, for example, or when we release a lot of water into the system from northern part of the watershed, that's when the communities get mixed in the water. So windy conditions pretty much mix everything easily in a lake because it's a shallow lake that easily gets disturbed. So you can see that basically even though Microcystis aeruginosa dominates, when we have windy conditions, we can determine what is actually dominating the community. But based on the samples that we actually analyze under microscope, we know it's Microcystis aeruginosa. So here is, so what is the role of nitrogen or nutrients in cyanobacteria bloom dynamics? So here is a ratio between dissolved inorganic nitrogen and TP. So usually when this ratio is around, it's below about 2.5, that's when we have nitrogen limited conditions. And on this axis, we have toxins. Now I'm blind, that's another complication here. We have turbidity and also number of blooms. So you can clearly see that we have more turbid conditions during the dry season. The winter storms pretty much mix everything in a lake easily. We have very low concentrations of nitrogen in a system during the wet season. So we have limited conditions during the wet season, and this is because the nitrogen is taken up by cyanobacteria from the water. So once the blooms start, once the water gets warmer, around I would say late spring, end of April, the biomass will start increasing, of cyanobacteria start increasing, and that's when the dissolved inorganic nitrogen and also phosphorus they decline steadily until I would say end of August, and then the biomass, the concentration of cyanobacterial cells slowly start decreasing towards the end of the bloom season, and that's when the DIN is again increasing. So that uptake has significant effect on nutrient dynamics in the lake. Okay, so let's go. Oh, one more thing, I did also just look at the correlation between nutrients and chlorophyll A and toxins. And again, there are significant differences, regional differences. The strength of the correlation is not going to be the same. So usually the uptake is higher in those northern regions. And that is basically when water from canals enters the lake and the nutrients are quickly removed by phytoplankton. And again, this central zone has the lowest uptake rate, and this is because of that light limitation that I talked about earlier. Oh, wait. Whoops. Well, it wants me to go to a cyanobacteria mitigation now. Okay, so we are switching gear from the monitoring to more applied things. Like I mentioned, we also try to prevent transport of toxic blooms into estuary. So how do we decide whether to treat the water or not? So we develop a decision, I don't want to say tree, it's a path that we use. So first of all, we look where the blooms are concentrating using cyano maps. The next step is to send the crew to the field to visually assess the situation, because this is done because treatments are expensive. So we don't want to spend money if we don't have to. So there's a visual assessment of the conditions present at those priority areas, which are the outflow structures and the major marinas. And then the crew enters the data into the 1 to 3 survey, and then we develop a bloom index. And based on the area of the bloom and severity of the bloom, we decide whether to treat or not to treat. So when the blooms are severe, we send the crew, again, those are contractors that we hire, to apply hydrogen peroxide-based algaecide products. So our product, the product that we use right now is called Lake Oxy. It's a hydrogen-based product. So here's a few examples of our successful treatments. So one that we did was at the Pahokee Marina. So you can clearly see that marina was heavily affected by the blooms. So that bluish color that you see is basically decomposing cyanobacterial biomass, and the phytocyanin pigments are slowly released from the cells, and the toxins are also released from the cells. So basically, we had really toxic blooms that were slowly decomposing within that marina. That marina is big, but it's very enclosed, so it traps all the bloom inside the marina, where we did some improvements, but initially the blooms had no place to go. There were no openings, and they were literally trapped there. They start decomposing, releasing toxin. And what is important to mention, the toxins can aerosolize, so we can actually inhale them. So, and believe it or not, some people were actually living on those boats. And we did warn them that it's not the best place to sleep. But they decided to stay anyway. But anyway, we actually took we developed a strategy how to basically deal with that bloom. But the stagnant condition, low DO, nutrient-rich waters, and constant supply of biomass from external sources, meaning the lake, is basically the reason why we had the situation at the marina. So how did we deal with it? So this is basically before the treatments, and this is after the treatment. So you can clearly see the improvements. And we also we had 4 monitoring stations. So we installed exoprobes there. So we're monitoring water quality continuously at those 4 locations. And we also collected samples for nutrient analysis, toxin analysis, and quick assessment of what is actually present in the water in terms of species. And we also installed the ultrasonic device at that location. That was one additional thing that we use. So here's how the marina looks from the air. So you can see that this is the entrance point, and this is the wall that protects the marina during the storms. So you can see that there's just this tiny entrance, and we had one outflow point. but that water was not moving. There was like no circulation. It was a very stagnant water, full of nutrients, full of biomass that was slowly decomposing and releasing toxins. So what we did, long-term improvements included removal of pieces of sheet pile that form the protective wall. And we did it at the points where usually we saw some high accumulation of biotoxins and biomass. So this point and this point, and that was the third original point that was already there. And that improves slightly the movement of water that basically allow the water to move out and take the biomass with it. So that was one improvement that we made. Another thing, because the biomass was really thick, so we hired a contractor with a gigantic vacuum, and we physically removed that biomass, like vacuumed it out of the marina. And so the solids were separated from water in the container that you see here. And then solids were taken away to this state-owned landfill where they were disposed of. And then the water was treated with ozone, which is a strong oxidizing agent. It's often used at the treatment plants. So, and the water after the treatment was returned into the marina. So this is the effect before and after. So the treatment was pretty successful. And we installed also circulators to help water move around. And this is it's ultrasonic transducer that we're testing at the marina. We also use algaecide product, hydrogen-based algaecide products, and aerators. So we're pumping air into that water to help with a dissolved oxygen issue. So we use different strategies to get rid of that bloom throughout the 2021 bloom season. So how the transducers work? So basically, the transducers are producing high-frequency ultrasound waves, and they produce the cavitation bubbles, and the bubbles grow and burst, and that releases a lot of energy and affects the gas vesicles within the cyanobacteria cells, like microcystic cells. So what they do, they literally just are removed from that photic zone, they sink to the bottom and decompose, and they're pretty much destroyed. And toxins are also degraded. Sometimes we see when the walls break completely, we can see some leakage of toxins. So immediately after the treatments, we can see some spikes in toxins, but over time, the toxins will decrease. So this is one of the cool things that we're testing at the marina. And here are the results. So microcystin toxins, so you can see that before the treatment, high concentrations of toxins. And at the peak of that bloom, the concentration was 800 micrograms per liter, okay? And remember that the EPA threshold is 8 micrograms, so it was 100 times higher at the peak of that bloom within that marina. But you can see that we successfully removed not only biomass, but also toxins from that marina. So I would say that these multiple strategies combined together and applied at the same time definitely did the job. And one more product that we use is a hydrogen peroxide-based product called Lake Oxy. And it's a granule product which is approved by US EPA. And it's basically a sodium percarbonate. So when it enters the system, it decomposes into sodium carbonate and then and also hydrogen peroxide. And over time, hydrogen peroxide decomposes into water and oxygen. So it's an environmentally friendly product. So you end up with water and oxygen. There's no chemical that we are adding into the water. And so again, it's a strong oxidizing agent. It reacts with cyanobacteria population. And what is cool about this is it's causing a programmed cell death, which is basically the whole population collapses. Okay, so this is basically, it works really well. And we can see a result within 24 to 48 hours. And this is exactly what we need in our system, which is infested by those terrible blooms. And another example from, this is the C43 canal that connects the lake with Caloosahatchee. So we did 112 treatments along 48 miles of the canals and and you can see that this is the product that was released. So it spreads with currents and winds, and that's how basically it works throughout the area. So it's a pretty good product. So it's not a liquid, it's actually granule product so it takes time for the hydrogen peroxide to be released. And then, so it basically works on the biomass over time, which is exactly what we need here. Just to show you also results from one of the sites, this is the structure, this is the lock. So basically that's where the boats are getting in and out. And so this is the Franklin Dam, which is the last structure on the C43 canal right before the water from that canal is released into Caloosahatchee. And so you can see that before treatment, we had over 300 micrograms per liter concentration of toxins in the water. And right after, the toxins dropped to almost undetectable levels. So again, the treatment was pretty successful, and you can clearly see it also on these pictures. Blooms, no blooms. And the same was done at the S308 canal on the other side of the lake, which is right here, another major outflow. Again, before and after concentration of microcystin toxins. So again, the treatment work. And this is from this year. So this is what I was talking about. The winds were pushing the biomass, and they were accumulating against the structure and the lock. And so you can see it clearly on the map. And this is the bloom index. So the higher, the maximum bloom index is 12. So you can see that we had high biomass accumulation present throughout the year. And we did the treatments with Lake Oxy at those locations. And this is before the treatment and after the treatment. So again, the treatment worked. And one more thing that we're planning for this year, but we're still working with our partners from ERDIC, which is a research branch of the Army Corps of Engineers in Vicksburg. So we are going to work, we developed already the project that we are hoping to start this year, but the Corps is finalizing the paperwork. So we're hoping to start it next year. So we're going to do more quantitative studies and test the product under different flow scenarios. So sometimes we have to, the previous treatments were mostly done in more stagnant water, but we want to test if we have to release water at a certain flow rate, how well that product is gonna work, and how much product we will have to apply. So how much we apply depends on how much biomass we have, but also how fast the water is floating, right? So basically, we want to do those treatments and maybe develop some kind of model that will help us plan those treatments better and save more money, because those applications, like I said, are not cheap. So we want to be efficient. And this is the last thing that I have, is basically the modeling. So like I said, these groups are developing forecasting and modeling, forecasting tools that we want to use for better operational decision making. So basically, it's a work in progress, and our team is working with Google team. And but the most advanced work that was done by NOAA. So this is still work in progress. So I just want to mention this. And this is the whole team. So we got a BG Team of the Year award. These are all the bureaus at the district that are involved. So it's not one-man job. Okay, it takes it takes a village to manage Lake Okeechobee Cyano-HAB monitoring and prevention mitigation program. And not only different bureaus and dozens of people, but also two of our partners, FDEP and Army Corps of Engineers. All of us work together to make those things happen. And it's not an easy task. There's always someone who's not going to be happy. So that's what I have. I apologize for the technical difficulties that we have, but this is basically the work that I want you to know about. So that's it. Thank you.